So let's consider a shell of radius r that carries uniform surface charge density sigma. So, in other words, there's positive charge uniformly distributed on the surface of the sphere, but nothing inside. And we want to evaluate the divergence of the electric field everywhere. So we need to know what the electric field is. Well, we know that this is rho over epsilon naught. So, right, we know that the charge is not zero here, and so should be the only place, right, on the surface of the shell is where this quantity should not be equal to zero. So let's evaluate the electric field. Right, given the uniform distribution, we know that by Gauss's law, we can integrate over a closed surface of radius r, let's say r less than r, to get the electric field inside the shell. And so we integrate, we get 4 pi little r squared. That's the left-hand side of Gauss's law. The right-hand side is the charge enclosed, which is 0 over epsilon naught. And so we know that the electric field inside there is 0. Right, a perfect conductor, the electric field inside is 0. Outside is just going to be the electric field produced as if all the charge were at one location. Of course, from Gauss's law, we can do the same thing. In this case, we have r bigger than r, or equal to r. And then on the right-hand side, we have all the charge inside, which is sigma times 4 pi r, capital R squared over epsilon naught. And of course, that gives us the electric field of a point particle of 4 pi r squared sigma over 4 pi epsilon naught r squared, r hat, and that is sigma capital R squared r hat over epsilon naught variable little r squared, right? The electric field of a particle of charge sigma times 4 pi r capital squared, all at the center here. Okay, so we have our electric field. So now we can do the divergence of the electric field. Let's do it for r greater than capital R, right? We know this is going to be 0. Let's confirm this, right? In spherical coordinates, it looks like this. R squared, the radial component. This only has a radial component, so it's 1 over r squared d by dr of, right, little r squared times this. So that's just sigma capital R squared over epsilon naught. And that's just a constant, so we can see that this is equal to 0, as it should be. For r less than r, we have divergence of E is just 0, because the electric field is 0. So we have derivative of 0 with respect to anything is still 0, and so that makes sense. But at r equals capital R, right? In other words, divergence of E at r equals capital R gives us 1 over r squared, and then we have this derivative. So we're considering the limit as epsilon goes to 0 of r squared ER, so that's capital R squared sigma over epsilon naught. Right, the derivative with respect to r, so it's this minus 0 because the electric field, so let's just write that, right? It's the ratio, it's the limit as epsilon goes to 0 of the value outside and inside as we cross this boundary over epsilon. And of course, epsilon goes to 0, so this tends to infinity. And so the divergence of the electric field is everywhere zero except here where it becomes infinite. So you always see these infinities when we have these distributions of charge over somewhat unphysical situations, right? This is not this isn't a density. It's a perfectly thin shell of charge, which is a little unphysical.